So hopefully you've got the opportunity to go through this, take notes. I would encourage you to, whenever possible, pause the video and try to work the examples out on your own prior to me working up. I think that you'll find that beneficial. Okay, so let's go ahead and get started here. So in this section, we're going to talk about the maximum and minimum values of a function. Sometimes these are called the extrema, or extreme values of a function. So we're going to define two different categories. The first category are called the global extrema, or sometimes called the absolute extremum. So let's pick a number, any arbitrary number, in the domain of a function f. So if it turns out that that number we picked is the largest y value, has the largest corresponding y value in the function, then we're going to call it a global maximum. So we're going to say that an absolute maximum f is f of c if f of c is greater than or equal to f of x for all x in the domain. So we'll look at a picture here in just a second. But remember, interpret these as y values. So if I have a function here, let's just go ahead and put a picture up, I guess. If I've got a y value here, right here, this y value would be my f of c in this problem. Okay? Notice that the y value is greater than or equal to all of the other y values for this function. So then we're going to go ahead and call it a global maximum. We'll understand the word global, why are we saying that here in a little bit. Okay, similarly, we have a global minimum. And a global minimum is some value c where f of c is less than or equal to f of x for all x in the domain. Okay. So now we've defined global extremum. In fact, let's scroll down real quick and let's look at this function here. So for this function here, I want to go ahead and identify the global maximum and global minimum, if there are any. And in this case, there are. So we would call this value right here, this is a global max. Okay, so that, let me just be a little more vague here. Let me say that this point right here is a global maximum on this function. And this point right down here is a global min. Meaning of all the y values that show up associated with domain values in the function, this y value right here, negative 27, is the smallest y value. Likewise, of all the y values that show up in this function, for any of the x in the domain, this is the greatest y value. So that point right there would be labeled as a global maximum. Okay. Now, we also want to introduce what are called local extrema. Local minimums and local maximums. So these occur not on the endpoints, first of all, and you don't have to be the largest or smallest value in the entire domain of the function. You just have to be in a neighborhood. So let's go ahead and define this. Let f be a function with a domain D, and let C be an interior point. The word there is interior, point in the domain. This is important. Not all books choose to define local maxes and mins this way, but this is the way our author does. So I'm stressing that this needs to be an interior point. Okay. Then we would say that f of c is a local maximum if f of x, if f of c is greater than or equal to f of x, not for all x in the domain. This is where the definition is going to be different. Before we said it had to be for all x in the domain. But here we're going to say for all x in some open interval. Interval containing c. So there's some similarities and some differences to the definition of a local maximum as opposed to a global maximum. Okay. So you still have to be the greatest y value around, but only in some open interval containing the point. So let's go down here. Let's look at this function right here, and let's see if we can identify a local maximum. Okay? Well, first of all, I cannot pick x equals -1 to be a global or to be a local maximum. How come? Because we said that it had to be an interior point. So we cannot include x equals -1. But there is a local maximum in this problem, and in this case we would say that this value right here is this point right here is a local maximum. Okay? How does this meet the definition? Well, first of all, notice that there are plenty of points. You know, for instance, this ordered pair right here, or this point over here, where the y values are greater than the y value at what we're calling our local max. Okay? So greater than this y value right here. But I can put an interval around the x value c. Okay, here c in this case would be 1. And around c I can put an open interval, and notice what happens there. On this open interval, let me see if I can switch. On this open, no, you're not cooperating. On this open interval, we see that f of c is the greatest y value around. Okay, and now let's look at the definition of a local minimum. So a local minimum is going to be very similar to the definition of a local maximum, except we're going to reverse the direction of the inequality. So C will give the location of a local minimum if f of c is less than or equal to f of x, again for all x in some open interval. Containing c. Okay. So it doesn't have to be a local minimum. You don't have to be the smallest point in the entire function. It just has to be possible to construct a neighborhood around that value c so that it is the lowest value in that neighborhood. Okay. So let's look down here. Let's see if we can identify any. Local minimums. So it appears to me that we have a local minimum right here. So conceptually, folks, all we're saying when we're saying something's a local minimum or a local maximum is we're identifying the peaks and the valleys. That's a good way to look at it. But there's a precise math definition that we're using here. We're saying that c equals 0 is a local minimum because I can construct an open interval around c so that it is the lowest value in that interval. Okay. Are there any other local minimums on this function? Take a look. Yes, there is. There's one other local minimum, and it's this point right here, which was also the global min on this function. How does that work? Well, if I construct an open interval around that point c, notice that for this particular open interval, at c equals 3, it is the lowest point in the interval, meaning take any other ordered pair from that interval, and all of them have y values that are either greater than or equal to this y value here at c equals 3. Okay. So hopefully that clarifies the difference between a global max and a local max, and a global min and a local min. Okay. So to be a global max, let's just summarize that. To be a global max, you have to be the greatest point around. Or in the entire domain of the function. So this is a global max because there are no other y values in the function larger than it. To be a local max, like we have here, you just have to be able to construct some open interval, like I did right here, for which that particular x value returns the highest y value in that interval. Okay. One other thing to keep in mind, and this is per our author's definition, that local maxes and mins can only occur at interior points, which means that although an endpoint may or may not be a global max or a global min, an endpoint can never be a local max or a local min. Okay, folks, so now I want to look at this point number 3 that I made. And this is potentially a confusing topic. That in that regards, the location of the extreme value versus the extreme value itself. Okay? So I'm going to try and parse that out here in just a second. So if we look at this function, the ordered pair 1, 5 is a what? Well, previously we said that it is a local maximum, right? That this point right here on the function we could call a local maximum. That's perfectly fine. But how do I distinguish between the number 1 in that ordered pair and the number 5 in that ordered pair? So we would say that x equals 1 is the location of a local maximum. So we'd say that f has a local max at that x value. So the key word here, and I've italicized it, the most important word there is at. That is the location of the local maximum. We could also say that f has a local maximum value of 5. So in this case, I'm emphasizing the actual y value that is the local maximum y value, the local maximum value. So that's a value of 5. So that's where we're trying to make some distinctions here. So I'd like you to now pause the video and work through 3a through f. Give that a shot, pause it, and we'll resume here in just a second. Okay, so we want to give the location of any global maximum. So in a previous version of this picture, I've already identified the global maxes, the global mins, the local maxes, the local mins. But this problem is asking us to give the location of any global maximums. So as you recall, and as you probably already have labeled, we said that we had a global max right here at this point. Okay? So the location of the maximum is at x equals 1. Oops, excuse me. Is at x equals what? Negative 1. Okay? That is the x value of the global maximum. If I asked you to give any global maximum values, then the global maximum value is the value y equals 37 here. The next question asks in C to give the location of any global minimums. Well, we have a global minimum at x equals 3. That is, if I go to this x value 3, I input it into the function, it gives me the lowest value in the function. But this is the location of the global minimum. D asks to give the global minimum values. So we have a global minimum of y equals negative 27. That is a global minimum value. So we have a local minimum at x equals 0 and at x equals 3. We have local maximums at x equals 1. Okay? So let's say a couple things now before we form any misconceptions. For this particular function, we only had one global maximum and one global minimum. That's not always going to be the case. We might have several global maximums and several global minimums. Okay? Likewise, in this example, we did have two local minimums, but only one local max. That's just function dependent, how many you have of each. The only thing I want to emphasize here is that the local extrema cannot occur at the endpoints in this class. Do I have anything else I want to say about this? Yeah, I guess the other thing is I will not purposely try to trip you up with this idea of the location being at a place and a maximum value of. I'm not going to try to purposely confuse you with that, but you should know the difference between the two. Okay. For those of you that are interested, there's a nice little point here that describes how different textbooks might choose to define their local and global extrema, and you can read through that if you wish, and if you're ever interested in that, feel free to come by and we'll discuss it. Okay, let's move on to the next page. So this next question asks us to give all of the extreme values for f of x equals the cosine of x, and to give their locations. So let's pause for just a second to remember what the cosine curve looks like. So the cosine curve, like all the trig functions, is periodic, and it looks something like this. Okay. You'll have to forgive me, I'm not doing the best of jobs, but that'll work. Okay. So let's go ahead and pick one local maximum, and it'll also be a global maximum. Let's look at this point right here. So what's this ordered pair? Well, this is the ordered pair 2 pi, comma 1. Whereas maybe down here for this local and global minimum, we have that this would be at the ordered pair pi, comma, negative 1. Okay. Well, notice that there's no coincidence that we picked those 2 points. All of these peaks and valleys would be local and global extremum. Okay. So convince yourself, take just a moment to convince yourself that, for instance, right here at the ordered pair pi over 2, comma 1, this is both a global max and a local max. Convince yourself of that. So why is it a global max? Because if I look at the range values of the cosine function, the largest range value in the cosine function is 1. There is no other input into the cosine function that will spit out something larger than 1. So that makes it a global maximum. Why is it a local maximum? That's a different question. And so if I were to pick some interval, like I could pick this interval right here, about what I'm claiming is a local maximum, notice that for all y values in this interval, it is the largest y value around. So that is why it is both a global max and a local max. Okay. All right, so let's go ahead and list them. And this is going to get a little bit messy. Hopefully I can fit it in here. I probably should have taken it to a different page. Let's see what we can do. So we have global max values are going to be 1. That is the maximum value that this function spits out. Okay? We also have local max values at the same place of the same y value, excuse me. What about the locations? Where do we have our global max values? They occur at, well, let's see, this one occurred over here at 2 pi, right? And there'd be another one right here. Where is this? This is at the order pair 0, comma 1. So that's at 0 pi, is one way to think of it. Down here I have, this is at negative pi, comma negative 1. And then I have another one up here at minus 2 pi, comma 1. Okay? So it seems to me that we have global max values at all of our even multiples of pi. Okay? So those occur at x equals, let's go dot dot dot, minus 2 pi, 0, 2 pi, 4 pi, dot dot dot. Okay? Well, what about for our local maxes and mins? Well, we've already said that those are exactly the same. So let's just say at x equals minus 2 dot dot dot, minus 2 pi, 0, 2 pi, 4 pi, etc. Okay, folks, and then let's note that we have for our cosine curve that we have global mins, and I'm just going to go ahead and say to save some writing, / local mins. Where were they? Well, those occurred at all the, well, let's say what the values were first. The local max and local mins were either, well, they were negative 1, and they occurred at x is equal to dot 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 minus pi, pi, 3 pi, dot dot dot. Okay? So I erased the graph to finish writing this out, but if you have any questions as to why that's so, look back at it or let me know. All right. So let's look at number 6 here. What we're looking at number 6 is we've got a function, a quadratic function, but in each instance I define the domains differently. And depending on what that domain is, it affects where we have global maximums and minimums. So one thing to notice that for just a moment, I'm only going to consider global maximums and global minimums. I'm not going to worry about locals for right now. We can talk about that in some of the later examples. Okay. So, so for this first example, we're looking for any global maximums and global minimums. Okay. Well, we have a global max at where? So actually now would be a great point for you to pause the video. Go ahead and try to identify the global maximums and the global minimums for each of these, and then resume the video once you think you've got it. Okay. So we have a global max at x equals 0. Let's write it this way, at x equals 0. Okay. That global maximum value is 4. Okay. We have no global minimums on this problem. So why is that? Well, this domain goes from minus infinity to infinity, and as we go further and further to the left, the y values become more negative. So letter B here, we're looking at this function. It is still that same quadratic, but now I've truncated the domain, and it's only defined between 0 and x equals 0 and x equals 2. It's only defined for these x values right here. Okay. And so then the question is what are the global maxes and global mins on this particular function? So we have a global max at x equals 0 of 4, and we have in this case a global min at x equals 2 of 0. Okay, so notice that I'm giving, in fact, let me go ahead and say these are what the y values are. This is of y equals 4 and of y equals 0. So notice I'm giving, in this case, I'm giving the location and the values. I'm doing more than the question said. The question just said to give the locations. So it's only looking for the x values here, but I'm going to go ahead and say just a little bit more about these. Okay? By the way, I'd like to add that there are no local maxes nor mins. Whereas in this first example, we did have a local max at x equals 0. Okay, let's look at C here. So for C, we have no global maxes nor mins, and no local maxes nor mins. And the reason why is because these functions are not defined on the endpoints. In this case, we're only defined between 0 and 2. And so pick what you think might be the, pick which x value you think might be the global max. Maybe you think it should be maybe this x value right here. Well, just by stepping slightly to the left, I can find another x value that's actually greater than it. And I can keep doing that because this is an open interval. Okay, let's look at D. So in D, we have no global max, and we have a global min at x equals 2 of the y value 0. All right. Okay, number 7 asks us to find any global extrema to f of x equals, in this case our function is the arctangent of x. So let's look at the graph of the arctangent. Do you remember what the arctangent looks like? In fact, maybe pause the video, try to sketch this graph on your own. Once you're ready, we'll resume. So remember that the arctangent is the inverse of the tangent curve, and we took a segment of the tangent curve. We took the segment between minus pi over 2 and pi over 2, which were the vertical asymptotes of the tangent curve. And so then the arctangent has horizontal asymptotes at those two locations. So we have horizontal asymptotes at pi over 2 and at minus pi over 2. So if we look at the graph of the arctangent curve, it looks something like this. And so here we see that there are no global maxes and there are no global mins. Okay, I don't know why I'm putting an apostrophe on maxes or mins. Okay. There are also no local. So let's just add that. But we weren't asked to find whether there were any local extrema. We were only asked for global extrema here. Okay, so let's just clarify. Again, pick any x value on here. If I picked that x value and claimed that that was a global maximum, well, what could I do? I could just simply pick an x value further to the right and find a y value that was slightly higher. I can do that everywhere, and so there are no global maximums. The same argument holds for the global minimums. Okay, so let's continue. At this point, we've had only one or two named theorems in this class. So this is our next big named theorem. We've got the extreme value theorem. And what the extreme value theorem tells us is this. We want to find the global maxes and global minimums of a function. Okay, we want to know where they have the largest y values and the smallest y values for a given function. But we've already seen, in fact, if you look up there at example 11, examples where functions don't have extreme values. Okay? So we want to know what conditions are necessary to require that the function have a global maximum or global minimum. Okay? So this theorem sets those conditions. It says that as long as f of x is a continuous function on a closed interval, then it must attain both its maximum and its minimum at some point within those intervals. So let's go ahead and real quick, let's just jump up here. Notice that letter D, let's go all the way up to letter C up here. Letter C, we had no global maxes nor global minimums. Why is that? Well, I'm looking at this function. I do see that this function is a nice continuous function, right? So we've got a nice continuous function, but we have no global maxes or mins. What's the issue? Well, if we go back and we look at the conditions for the extreme value theorem, it said not only must x be continuous, but it must be continuous on a closed interval. If we go look at this interval up here, we notice that this interval was not closed. Okay, so number 9 on the next page asks us to go ahead and give an example of a function that is not continuous on a closed interval that doesn't achieve its maximum. So what are we doing here? So for 8, we specified the conditions that require f to have a global max or a global min, or both. Well, both, but we're looking specifically at maximums here. So what does f have to be to guarantee you always have a global maximum? Well, one is that f must be continuous, and the second is that it must be on a closed interval. We already looked at one example of where this might fail if we lack one of those two requirements. Okay? So number 9 here says, come up with a reason why we actually require f to be continuous. How come it says f has to be continuous in the statement of the extreme value theorem? Well, let's see if we can come up with a function that is on a closed bounded interval, but that isn't continuous. Okay. So we want a function that's defined on a closed interval, but we don't want it to be continuous, and we want to show that it doesn't have a global maximum. Well, let's take this function right here, for instance. Okay. Notice that this function is defined on A to B, right? This would be my A in this case, this would be my B. It's defined over this whole interval, okay? And the interval is a closed interval, right? But where does it break down? Well, it's not continuous, and notice that it does not achieve its local max, okay? In this case, so here's a case of a function that's not continuous and does not have a local global max. In this case, f doesn't have global max. Okay. Number 10 asks us to go ahead and look at the second condition. It says go ahead and find a continuous function, but it's only continuous on an open interval that doesn't achieve its maximum. Okay. So we already looked at one example. That was this parabola right here. Remember this one from the previous page? That it's continuous on the interval from A to B. Let me go ahead and kind of make that a little bit easier to see. So we had, it's defined from A to B, but not at the endpoints necessarily. And this function doesn't attain its local maximum. Excuse me, global maximum. Folks, I said local and I shouldn't have. I meant to say global. Okay. So this function does not attain its global maximum. So we saw that example on the previous page. Let's give one other scenario where this might break down. Let's pick this interval right here from A to B, and let's define a function on it that looks like this. Okay. Let me pause the video. So folks, I paused it just to erase. I wanted the asymptote to be a different color to make it a little bit easier to see. So here we have a function that is, one, it's continuous, and it's continuous on an open interval, but because that interval is open, it does not achieve its its global maximum, okay, because of that asymptote. So think about why that's the case. But what am I trying to explain? Well, in examples 9 and in examples 10, we've explained why the extreme value theorem requires two conditions, that f be continuous and that it be continuous on a closed interval. So in each one of these, in 9, we looked at what happens, where could the theorem break down if it wasn't continuous, and in 10, we looked where would it break down if it was continuous, but not on a closed. All right, folks, so I want to go over something now called Fermat's theorem. And this is a useful theorem that we're going to need it to build Rolle's theorem, and we'll use Rolle's theorem to build the mean value theorem. So we're laying the building blocks for one of the big results of calculus. This is Fermat's theorem. Be careful for those of you who know your math lore. This isn't Fermat's famous last theorem. This is just another math theorem. Okay, it's not the famous one that was solved by Andrew Weil. So what does Fermat's theorem say? Okay. It says, suppose f has a local maximum or minimum at some point c. Okay. There's a lot to unpack there. We've got a function. Okay. At some point c on that function, we know we've got a local maximum or a local minimum. By the way, we actually know one other thing, because our author said that local maximums and minimums can only occur at interior points, so we know that we're talking about an interior point on the function. Okay. So that's the first thing. Okay, if we have that, and second, if the derivative exists, then the conclusion of Fermat's theorem is that the derivative must be 0 at that point. Okay, so I'd like to see if we can get an understanding of Fermat's theorem by looking at a graph here. Let's see how we can do making this graph. Let's go like this, and so here we've got a function. It's kind of an interesting looking function. Let's call it f of x. Okay. So first of all, we're only going to consider interior points. So we're we're not going to consider this. Because we're only interested in local maximums, minimums. Those have to occur at interior points. So let's look at the first condition. Let's find out where f has local maximums and minimums. Well, f has a local maximum right here, and it has a local minimum right here. It also has a local minimum right here and a local maximum right here. Okay? So again, in all of those instances, what am I able to do? If I'm going to call it a local max or a local min, I've got to be able to draw a neighborhood around it so that for all y values in that neighborhood, if it's going to be a local minimum, it's got to be the lowest point around. Okay? Or if it's going to be a local maximum, when I draw the neighborhood, now careful, can I draw my neighborhood out here? Nope. Better move it in a little bit. Okay? For all y values that I plug in, if this is going to be a local maximum, it has to be the greatest of the y values. Okay, that's just a quick summary. Okay. So we can do the same thing here. We've got a local maximum, and the same thing here. We've got a local minimum. Let's go ahead and call that C1. We'll call that C2. We'll call this C3, and we'll call this C4. Okay. So let's see how Fermat's theorem either applies or doesn't apply at each one of these points. So Fermat's theorem, and first we say, let's find where we have local maximum minimums. We found those C values. Then the second condition is that f prime of C exists. Okay? If we've satisfied both condition 1 and condition 2, then Fermat's theorem says that the derivative must be 0 there. Okay? So let's look at what I've called C1. Okay? Well, at C1, we do indeed have a local, in this case, maximum. And does the derivative exist at C1? Yes. Notice this function is nice and smooth around C1. So we can take the appropriate limit that we need to calculate the derivative. So f prime of C does exist. So what is the big conclusion of Fermat's theorem? At that point there, the derivative must be 0. Well, we look at the graph, and sure enough, it is. Okay? Similarly, if we look at what I've called C2, in this case, C2 gives us a local minimum. It is differentiable there. And what is the derivative? The derivative is 0. Okay? Let's look at what I called point C3. At C3, I meet the first of the two conditions for Fermat's theorem. I've got a local maximum or minimum. In this case, it's a local maximum. Okay? The second condition, though, says the derivative must exist. But what do we know there? Well, there I've tried to draw. It looks like I hope it looks like a corner. If it looks like a cusp to you, that's okay. It'll still work. But it's supposed to be a corner, and at that corner, it's not differentiable. Remember, that was one of our conditions for. That was one of our scenarios that we saw where a derivative wouldn't exist, even though we were continuous. So even though we're continuous at C3, the derivative does not exist. So Fermat's theorem does not apply because we failed to meet this condition. So let's just say here, Fermat's doesn't apply. I'll put DNA for does not apply. Okay. Likewise here, Fermat's does not apply. So even though I have a local minimum at C4, since it's not differentiable because of that cusp, then we can't conclude that the derivative is 0, and that should make sense. Okay? So what does Fermat's theorem say? It says that the phenomena that we see in this graph are true universally. So it's not limited to this graph that I drew. It is always true that if you have a local max or min at a place and the derivative exists there, then the derivative must be 0. Okay, number 12 asks the next question. Is the converse of Fermat's theorem true? So let's go back and look at Fermat's theorem. Okay, so Fermat's theorem said if we have a local max or min at some c value and the derivative exists, then the derivative must be 0. So the converse of that, okay, which is not, we'll find out is not true, but let me just say what the converse would be. The converse would say if f prime of x equals 0, does that imply that f has a local max? or min at that point. That's what the converse would say. Well, it turns out that the converse is false. Okay? So let me give you a graph that illustrates why the converse is false. Let's look at the graph of, let's look at the graph of the cube root, or excuse me, the x cubed function. So here's a graph of the x cubed function. Okay. And notice what happens at x equals 0. At x equals 0, what is the derivative? So f prime of x here equals 0. Okay. So here we have a place, let me put that in a different color. Here we have a place where the derivative is 0. Do we have a local max or min there? No, we don't. We've just got what's called an inflection point there. We'll talk about that later. But here we see an example where the converse of Fermat's theorem is not true. So just because the derivative equals 0 does not mean you're going to have a local max or min. Remember what Fermat's theorem said, though. It said if you have a local max or min and the derivative exists, then that derivative must be 0. Okay, so let's continue. Number 13, we're going to define what we mean by a critical number. Okay? So our definition that we're going to be using for this class says let C be an interior point. Where there is interior. Let C be some interior point of the domain. Then we say that C is what we're going to call a critical number. Folks, I may sometimes get sloppy and call it a critical point, but I really should say critical number. We say that C is a critical number of f if f prime of C equals 0 or f prime of C does not exist. So there are two conditions we must consider if we're going to be looking for critical numbers. Those are going to happen where the derivative is 0 or where the derivative does not exist. Okay? Now, this whole course I've been harping on the idea that just because that when an expression is 0, that does not mean it does not exist. Those are two completely different ideas. But here, if either one of those happens, then we're going to go ahead and say that we've got a critical number. So we have two separate cases that we must consider where the derivative is 0 or where the derivative doesn't exist. If either one of those happen to an interior point, then we're going to go ahead and call it a critical number. Okay? I don't think it's, I said more commonly, I'm not sure if that's true, but in a lot of other calc books, they just simply say let C be in the domain, which means that critical numbers could occur at the endpoints. So I just want to point that out to you, but we will be using definition 13 here that says that it must be an interior point. Okay, folks, so this is number 15. I have moved it over to its own page, and we're asked to find all critical numbers to this function right here on the interval from minus infinity to infinity. So just to recap, what were our critical numbers? Well, our critical numbers were places where the first derivative was either 0 or the first derivative did not exist, provided that was an interior point on the domain. So in either case, if we want to find critical numbers, we're going to have to look at the derivative of this function. So let's go ahead and differentiate this. So folks, looking at this function, notice that I've got a product. So I'm going to have to use my product rule here. Okay, let me call this the first. I'll call this the second. So we get that f prime of x is equal to the first times the derivative of the second plus the second times the derivative of the first. Okay. So real quick, in terms of our derivative, this was the first, this was our d second, plus this is our second, this is times d first. If you're confused about how we took the derivative of that first term, if you're confused about how we came up with this, if you're confused about how we came up with that, what did we do? Well, we said, okay, the derivative of 3/5 x, excuse me, x to the 3/5 power. Here we go. How do we find that derivative? Well, we bring down the power, or we multiply by the power from our power rule, and then what do? We subtract 1. We subtract 1 from the power, but that is x to the 3/5 minus 5/5, which is how we got 3/5 x to the 3 minus 5 gave us negative 2/5. So that's how I did that derivative right here. Okay. So taking the derivative is actually the easy step in this problem. We now want to figure out where this derivative is either undefined or where this derivative is 0. So if I want to do that, I need to go ahead and combine it as a single fraction. So what I'd like to do first is let's go ahead and reorder this as 3/5 x to the minus 2/5 times 4 minus x minus x to the 3/5. And if you're feeling good at algebra, I encourage you to pause the video and go ahead and work your way through this, combining it as a single fraction. Okay, so I do encourage you to try it and then then resume. So we get 3/5, 3 over 5 times x to the 2/5 power when I bring that x down below. And in the numerator, we'd have 4 minus x. Multiply that. So all I've done there, folks, is rewrite this. And it's not going to delete that quickly. All I did was rewrite that term. And what did I do? I went ahead and brought this this x term, I brought it down below the line. And so when I did so, I changed the sign on its exponent. Okay. And then I went ahead and multiplied the 3 to this parentheses term here. Okay. Minus x to the 3/5. So what have we got? Well, we've got two terms. One of them is a fraction, and I'd like to combine them together. So to do so, we're going to need to get a common denominator. Well, our common denominator then will be 5x to the 2/5 power. 5x to the 2/5 power. Okay, let's go ahead and clean that up a little bit. So the first term we'll leave alone. Let's distribute that 3 through, so we get 12 minus 3x all over 5x to the 2/5. And then in the denominator of the second term, shouldn't be a problem, we've got 5x to the 2/5. But the real question is, what do I get in the numerator? Well, in the numerator, first of all, I'll have that factor of 5. And then off to the side, I'll calculate this. Notice when I multiply x to the 3/5 times x to the 2/5, well, that's x to the, add them together, and I get 5/5, which is just x. So this is just a 5x here. So at long last, we've got two fractions with a common denominator, so we can go ahead and just add their numerators. And so I get 12 minus 8x all over 5x to the 2/3. And now, finally, we get to return to the question. Okay, that was quite a lot of work, and unfortunately for these critical number problems to be any interesting, they often have to involve simplifying large, complicated fractions. Okay? So, as a reminder, we're after our critical numbers here. And what did we say that the critical numbers were? We said that the critical numbers were the places where the derivative was either 0 or where the derivative didn't exist. Okay? So, this is the derivative, f prime of x is equal to 12 minus 8x all over 5x to the 2/3. So let's answer the question, where is f prime of x equal to 0? What x values could I plug into the derivative so that it would spit out a 0? Okay. Well, the derivative is a fraction, right? When is a fraction equal to 0? So I guess I can go ahead and set the fraction equal to 0 if you want. All over 5x to the 2/3 equals 0. But when is a fraction equal to 0? A fraction is equal to 0 when its numerator is 0. So that would happen when 12 minus 8x is equal to 0, or when 12 is equal to 8x, or when x is equal to 12/8, which reduces down to x is equal to 3/2. So that is a place where the derivative is 0. So what did we say for a critical number? We said a critical number is a place where either the derivative is 0 or it doesn't exist. So this is where f prime of x equals 0. So it's a critical number. Okay. But then let's also look at where the derivative is undefined, because there's two ways you can get a critical number, where the derivative is 0 or where the derivative is undefined. So f prime of x is undefined if what? Well, what operations am I doing that could get me into trouble? Well, the only operation that I'm doing that could get me into trouble is the operation of division. All of those other operations are defined for all real numbers, including taking the 2/3 power, right? There's nothing wrong with taking the 2/3 power of any type of number. I can take 0 to the 2/3, I could take 8 to the 2/3, I could take -8 to the 2/3. So that's not a problem. What is a problem is the operation of division. So we need to make sure we don't divide by 0. Okay? So when would we divide by 0? If the denominator came out to be 0. So f prime of x is undefined if the denominator is 0. Okay, what's our denominator? Well, it's 5x to the 2/3 equals 0. So I'm not going to do any algebra for this. When is this expression equal to 0? It's equal to 0 if x is equal to 0. Okay? So that means that f prime is undefined. If x is equal to 0. So x equals 0 is also a critical number. Okay? But this is because this is where f prime of c did not exist. Okay? So the justification for why x is equal to 3/2 is a critical number, and the justification as to why x equals 0 is a critical number, those are two separate justifications. So, in summary, let's flip back to the previous page. We were asked to find all critical numbers. Okay. We have critical numbers at x equals 2/3 and at x equals 0. Okay. And I just want to reemphasize this is where f prime of x equals 0, and this is where f prime of x is undefined. Okay. The justification is on the other page. Okay. Okay, so we want to find all critical numbers to g of x. So to do so, we want to know where is g of x, g prime of x, excuse me, equal to 0, and we want to know where does g prime of x not exist. Okay. So both those questions require us to know what g prime of x is. So let's go ahead and calculate g prime of x. I'm going to do this one a little bit faster than before. So we've got a product rule. So here's my first times the derivative of the second. So what did I do there? I took the derivative of the square root function. Now technically the expression inside the square root is more complicated than just an x, so there's actually a chain rule there, and I multiply it by 1. But if you forgot that, I guess you'd be okay in this instance, because the derivative of x plus 5 is just 1. Okay, that was my first derivative of the second. Now here we go, plus the second times the derivative of the first. Okay. So let's clean that up a little bit. This gives me x squared over 2 square root of x plus 5 plus 2x times the square root of x plus 5. So our problem is similar to the last one. A lot of the work done trying to find the critical numbers involves simplifying some fractions. So let's go ahead and do that here. We're going to need a common denominator again. So my common denominator will be 2 over the square root of x plus 5, or 2 times the square root of x plus 5 over 2 times the square root of x plus 5. That's our common denominator. Folks, if it helps you to think about it, there's a divided by 1. Okay. So for that first expression, we'll leave it alone for the moment. So then multiplying this, we get plus, let's see here, this will give me 4x times x plus 5. Where did the radical go? Well, the product of the two radical expressions gives me the radicand. Folks, technically I should put an absolute value here initially. So I'll put that there, but then I'll promptly erase it. So technically there's an absolute value here, right? The square root of an expression times the square root of that expression is the absolute value of that expression. But notice that the domain of the original function, here the domain, although we didn't specify it, the domain is a set of x so that x must be greater than or equal to 5. Oops, excuse me, x must be greater than or equal to negative 5. So the expression inside the square root is already forced to be either 0 or positive. And so when I multiply the two square roots together, I'm going to have an expression that's always positive, so I don't need those absolute values there, which is why I can just go ahead and put a parentheses. Okay. All over my denominator of 2 square root of x plus 5. Okay. So now we have two fractions with a common denominator, so we can now add them together by adding their numerators. So let's see here, I'd have an x squared, and then when I distribute this, I'd have another 4x squared. So in total, that gives me 5x squared. And then I'd have plus 20x. All over 2 times the square root of x plus 5. Okay. I would like to take one more step to factor the numerator. So let's go ahead and do so. This gives us 5x times x plus 4 all over 2 times the square root of x plus 5. Okay. So now I want to go ahead and find the critical numbers now that I've found the derivative. So again, we said f prime of x. I'd just like to recopy it. F prime of x is equal to 5x over x plus 4 divided by 2 radical x plus 5. So we have critical numbers where f prime of x equals 0. Well, when does that happen? That happens if x is equal to 0 or x is equal to minus 4. Those are the critical numbers I get from where the derivative is 0. Okay. And I found those simply by asking the question, where is the numerator of this fraction equal to 0? That happens at x equals 0, and again at x equals 4. Okay. The next question we ask is, where is f prime of x undefined? So this is a more interesting question. F prime of x is undefined if x equals negative 5. Okay. But if I go back to the domain of this function that we specified up here, I'm sorry I didn't highlight it so explicitly at the very beginning. There's the domain of this function. And so what do we know about negative 5? Well, even though negative 5 is a place where the first derivative does not exist, it's also an endpoint. Okay? So even though it's a place where the first derivative is undefined, that is, I cannot plug a negative 5 into that expression because that would result in a 0 in the denominator, it's not going to be a critical number. Okay? Now, folks, when you look at my test reviews, my exam review and my practice exam, at the time that I wrote those, I was using a definition from a different book which allowed critical numbers to be endpoints. So I would have said x equals negative 5 is a critical point. Okay? Critical points at endpoints aren't particularly useful places where the derivative is undefined at endpoints. That's not particularly useful anyway, so we're not going to be concerned about that. So what are the critical numbers of this function? Okay. So we have critical numbers at x equals 0 and at x equals 4, because these are the places where f prime of x is equal to 0, and there were no others. There was no place where f prime of x was undefined other than -5, but -5 is an endpoint. So in this case, we just have these two critical numbers. Okay. Number 17 is an interesting question, because here I'm asked to again find all the critical numbers of this function, but I'm asked to find the critical numbers on the interval from -5 to -1. So that should be a -4. Counting my mistakes, I'm about up to 38 by now. Okay, so we're now asked to find all the critical numbers to the same function on the interval from -5 to -1. So in this case, the only critical number is at x equals -4. 0, although it was a critical number when we just were considering the domain to go from from -5 to infinity. So 0 would be included as a critical number to that because it sits within that domain of the function. Okay. When I'm considering this restricted interval, then 0 is not in that, so I only have one critical number. That's at the place where the derivative was 0 on that interval. Okay. All right. So now we can say Fermat's theorem in sort of a nicer way. We can say that if f has a local max or a min at x equals c, then c must be a critical number. So that's just a restatement of Fermat's theorem, but instead of saying that the derivative has to, if the derivative exists and it must be 0, we know that either the derivative won't exist or it will be 0 there. Okay? All right, let's pause, because I'm in need of a break. Okay, so really the remaining exercises in this section involve finding absolute extremum. So what do we want to do if we want to find the global maxes and global mins of a function on a given interval? Okay. So step 1, find all critical numbers. Okay. Step 2 is we're going to evaluate all critical numbers in the original function. To find their actual y values. Step 3, and this is the step that students often forget, step 3 is evaluate the endpoints. And then step 4 is to simply classify the results. So folks, I'm giving you the steps before we try the problem, but that's okay. Okay. So let's look at number 20 here. For number 20, we are asked to find all absolute extremum for this function f of x equals x to the 5th minus 7x to the 4th plus 12x cubed on the given interval. So step 1, I'm looking up at these steps. Step 1 is to find all critical numbers. So here we go. Let's find the critical numbers. Well, how do we find critical numbers? Well, to find critical numbers, we look at where the function's derivative is either 0 or undefined. So let's go ahead and take the derivative of f. Let's go ahead and factor the derivative. Okay, so in fact, let me say this. Pause the video and factor this. I think you should all be able to do so. Okay. Pause the video and try it, because you'll have to do this on a test. Here it is in factored form. we get, let's see here, this would be 5x, and this would be x, and I'm not sure what the answer is. So we've got 1, and well, certainly one of these is 1, yep, and then 1, and 36, 2, and 18, and that's it right there, 2 and 18. So let's see, we put a 2 here, and an 18 here, and then let's see, we look at the signs, that's positive, that's negative, so I want both these to be negative. Okay, so there's the derivative of f. So the critical numbers are where f prime of x equals 0. Well, that happens where? That happens at x equals 0. Don't forget that at x equals 0. Okay. And at x equals 2. And at x is equal to 18/5. Okay. Now, one of these does not apply. Okay. So this is very important. This is an easy place to get into trouble. I was given the interval from x equals -1 to x equals 3. Okay. So I'm trying to find all critical numbers on that interval. So to do so, we took the derivative. Okay, check. I put it in factored form to quickly identify the zeros. Check. So we then found the zeros of the first derivative. Each one of these is a zero of the first derivative. But we're looking for critical numbers on this interval, and one of these numbers is not on this interval. Please don't think that just because it was the messy one, that's why we're excluding it. Okay? So we're excluding it because 18/5, if you simplify that down, 18/5 is a number a little bit larger than 3, which puts that critical number to the right of our interval that we're considering. Okay? Alrighty, so we found the critical numbers, did we? Okay. Why? Because f prime of x exists everywhere. So remember, there's two things that I'm checking always when I'm looking for critical numbers. I'm looking for where the derivative is 0, or where the derivative does not exist. But in this case, the derivative exists everywhere, so I only get critical numbers from that first source. So that's what's hard about these problems, folks, is that sometimes this is the only part that matters, but in a lot of cases you also have to consider where the derivative does not exist. So be careful with that. Okay. So now what are we going to do? Well, we've done step 1 and step 2. We've done step 1. We found the critical numbers. Now we're going to evaluate the critical numbers. I should have moved this to another page. We're going to evaluate the critical numbers in f of x. Okay? So let's see here. What is f of 0? Well, f of 0, if I plug a 0 into this function, and here I suggest putting it into the factored form of the function. By the way, if that were the case, I would give it to you in factored form like that. If I plug 0 into the factored function, I get 0. If I evaluate 2 into the factored function, let's see, I get 2 cubed times 2 minus 4 times 2 minus 3. So that is 8 times -2 times -1, which is equal to positive 16. Okay? So now we've evaluated the two endpoints. Now we've evaluated the two critical numbers in the function. Okay? Folks, everyone pause for just a second. What did I plug the critical numbers into? I didn't plug them into the derivative, right? If I plugged 0 into the derivative, or if I plug 2 into the derivative, I know I would get 0 because that's how I found them. I found the critical numbers by working with the derivative. Instead, what am I plugging the critical numbers into? I'm plugging them into... so we found the values of we plugged the critical numbers into the function. We now have the functional values when we plug those critical numbers into the function. So we've done step 2. Step 3 then is to go ahead and evaluate the endpoints. So now I'm going to look at specifically -1 and 3, and I'm going to go ahead and plug those into the function as well. So let's look at f of -1 and f of 3. So as you remember, I said it's easier to plug these into the function in factored form. So if I plug -1 into the function, let's see here, we'd have -1 cubed times negative 1 minus 4 times negative 1 minus 3. And if we simplify that, I think we get, so that would be a negative, and that would be negative 5, and times negative 4, so it's positive 20, but times the other negative gives us negative 20. And luckily this one's a little bit easier. If I plug a 3 into the function because of that factor, we get out 0. Okay. So folks, that's a lot of work. Let's just summarize. We know that f of 0 was equal to 0. We know that f of 2 was equal to positive 16. We know that f of negative 1 was equal to negative 20. And we know that f of 3 is equal to 0. Okay? So as a reminder, what are we trying to do? We're trying to find the global maximums and global minimums on this function. So we narrowed our list to a set of candidates. The potential candidates to be the global maxes and global mins were the critical numbers of the function and the endpoints of the functions. So I went ahead and plugged the critical numbers into the function, and I went ahead and plugged the endpoints into the function. Okay? So now we're ready to actually go through and classify these. Okay? So of them, which one gives me the global maximum? Well, of the 4 y values, 0, 16, negative 20, and 0, of those 4 y values, which one is the largest? It's right here, so this is the global max. And what is this y? What is the global min? It's this y value right here. So this is the global min. So we have a global max. Let me just give myself a little more room, and we'll summarize. We have a global max at x equals 2, max value of y equals 16. We have a global min at x equals negative 1 of y is equal to minus 20. Okay. Now folks, what's interesting about this is that the global maximum occurred where? The global max occurred at 2. Where was 2? 2 was a critical number of the original function. And the global min occurred where? The global min occurred at x equals negative 1, which was not a critical number, but was in fact an endpoint of this function. So let me clean this up just a little bit so we can read that. Okay. So we found the global max to be an interior point, and we located it by looking for the critical numbers. And we found the global min to be one of the endpoints, and we found that by plugging the 2 endpoints into the function. In just a moment, we'll look at a graph of all of this. Okay, folks, so what I've done is I've graphed our function in Desmos. This was the same function that we were working with, the 5th degree polynomial. And I've gone ahead and restricted the domain from x equals minus 1 over to x equals 3. Okay? So what we can see here is precisely what we discovered analytically, that the global minimum occurred down here. In fact, I can click on that point. The global minimum occurred down here at the order pair negative 1, 20. And the global maximum occurred up here at the order pair 2, 16. Okay? So these were the global maxes and global mins that we found on the previous problem. Okay? Just to reiterate what we did here. So our trick was to go ahead and find the first derivative. That's what I've just highlighted now in blue. That's the graph of the first derivative. And we found the critical numbers of the first derivative. That is, we found the places where the first derivative was 0, and over here at 2. Plus we found the places where the first derivative was undefined, which didn't apply in this case. So we had the 2 critical numbers. The 2 critical numbers were x equals 0 and x equals 2. Okay. And we decided we would plug those into the original function. But what else did we do? Well, we took the 2 endpoints, x equals negative 1 and x equals 3, because finding where the derivative is 0 doesn't help us if the extremum are on the endpoints. So we took each of those 4 values and plugged them into the function f. So that's where we got these 4 ordered pairs. We got the ordered pair negative 1, negative 20. We got the ordered pair 0, 0. We got the ordered pair 2 comma 16, and the ordered pair 3 comma 0. Okay. And by evaluating all 4 of those points in the function, we found where this function had its global max. We saw that this one, since the y value was greatest here, this was the global max. And since the y value was the smallest here, we said that at x equals -1, we had the global min. Okay? So again, it's sometimes hard to separate, or actually sometimes hard to put together the analytic part of calculus with the graphical part. So this is the picture for what we just did, where our work on the previous page, we said, okay, well let's, oops, come on. We said this is where the critical numbers are. We found at x equals 0 and at x equals 2. We plugged those critical numbers into the function, and we were able to identify, along with the endpoints, where we had global max and global min.